All right, so we're going to continue talking about modern physics here, and we have a really interesting experiment to talk about. And I think something that'll really help out is if you looked at the problems from the last section, and I went through and talked about this section, and I also did some of the example problems, particularly the swimmer problem. Turns out they didn't make us do it for no reason. So we'll talk a little bit about it. I'll try to explain it as if you've never seen it, but it might be helpful to rewatch it. So let me go over a few key points real quick. So first off, we were pretty confident that light had wave-like properties. That, you can observe the different properties of light, and it seemed properties. Light had this kind of wave-like property to it in the way that it moved, in the way that, particularly with Maxwell's equations. Maxwell's equations were huge, obviously, for unifying electricity and magnetism as really one and the same. But this is why Maxwell's equations are so awesome. Besides the fact that they unify two what we thought were different things, he also saw that the speed was 1 over the square root of mu naught epsilon naught, which showed that it was a wave. It was an electromagnetic wave. And at the time, it makes sense that light has to travel through a medium, because the waves need a medium. They need a medium. If you look at waves in the ocean, you need water to have the wave. If you look at sound waves, they need the air. And it was very reasonable to assume light needed a wave, right? So we came up with this term. It's called the ether. And we said the ether is the medium for light. Well, if that's the case, this medium must be everywhere, because we see light come from the sun to us. So for light to travel there, if it needed this medium, it must be between us and the sun and from the stars we see, because the light's coming there. And it has to be all over the earth because we can see light everywhere. So there must be this huge medium that light can propagate through. And this was the proposal. It was called the ether. Now, another question I want to ask, besides what the medium is does classical transformations work for light? Do classical transformations work for light? So we talked about Galilean relativity, Galilean transformations, classical transformation, classical relativity. And that was kind of the make sense idea. If you remember, we talked about it in the previous video. If something's moving, right, we have to consider that reference frame moving in addition to its velocity. So if you're swimming at a speed v, and there's a current u, your speed is v plus u, right? Makes sense. So does this kind of classical transformation work for light? You would think it would. If you remember, we looked at the example of the swimmer. One example was we have a current. What did we have? We had something like this, if I remember correctly. And there was a current U going this way, and he could swim at speed c. So he wanted to go here and then right back here, a distance of L. And this swimmer also wanted to go from here to here. These are also a distance of L. So they both travel to L, but in one case, it's going to be a speed of c minus u. Here it's c plus u, right? And in this case, he's going to kind of have to, if he wants to come right back, he's going to have to swim a little bit at an angle, right? And this is our v, and this is our u. And if you remember, to find this velocity, we did a little bit of trig. And then using distance equals rate times time, right? What did we get? We got, I think one was L over C minus U plus L over C plus U. And the other one was the exact same thing, except we had the square root in the denominator. Square root of something over something. I think it was like 2L over whatever it was. It was the exact same thing. So what I'm saying is this gave the exact same thing as this, except this part had a square root in the denominator, which means if you have it, you're going to have a smaller denominator. And if you have a smaller denominator, you're going to have a bigger number, right? So it turns out, that, well, you're going to have a smaller number. You're going to have a bigger number of the denominator, but a bigger denominator means you're going to have a smaller, number. So we found out, and if you can watch the video, I can go over it again, that this swimmer that goes straight across instead of left and right went faster. It went faster because of the way it was moving relative to the current. Now, this experiment we're going to talk about here, it was very, very, very similar because the ether can kind of be like a current. Another way to think about this is imagine we have this big train, right? And you have one guy here, and you have another guy here. Maybe it's you and your friend. Doesn't look too happy, but it's fine. This guy's tossing a ball, and then you get the ball and you toss it back. And you're both a distance of d. And let's say you both throw at a speed v. Well, if you're standing still, the time for the ball to go from here to here, we'll call that time 1, it's going to be the exact same time it takes to go from here to here, time 2. In other words, time 1 equals time 2. If you throw it at the same velocity and it's the same distance, it's going to be the same time. But let's draw another example here. Let's say it's similar. You guys are on a train. He looks a little happier there. They're all happy. And now the train is moving. So you have this resistance from the air, u, this vector. Who's going to throw it further? This guy or this guy? Think about it. Well, this guy is going to be throwing at this. We'll say it's the same distance d, and they both throw it at a speed v. Well, here it's going to go v plus u, right? And this guy, we'll do it in blue. That's going to be v minus u. So again, distance equals rate times time. If you have a smaller rate, which obviously the blue does, right? Distance over rate is your time. If you're going to have this smaller rate, that's going to impact the type of time it takes. So which one gets there first? Obviously the red one, right? Because it's going to be a bigger number. And a bigger number in the denominator means a shorter time. So if you're throwing it with the wind, it's going to get there quicker. Well, another way you can think of this is if you had a sun, and let's make this kind of elliptical orbit. And by the way, you could find out this speed. You could find out how quick the train was actually moving from here. And kind of similarly, let's say you have the blue planet, Earth here. And you have this ether wind. Obviously, it has to be all over because we're moving through it. There's no way we're going to be stationary, right? Because the Earth is moving, the sun is moving. You know, we're going to have all this stuff happening. Here, if you go to here, if you look here, surely we're going to be affected by the ether winds differently. When we're moving this way, we're moving against the ether compared to over here when we're moving with the ether. Well, you would think if you're moving with the ether, just like if you're moving with the current or with the the velocity from the air when the train's moving, that you're going to have a faster velocity, you know? Up here, when the train moves, right, you're going to have this wind. And when the earth moves, we're going to have this ether wind. It was what they called it, the ether wind. So hopefully that kind of at least makes some sense. The idea that it makes sense that there's going to be it makes sense that there's going to be, you know, some sort of ether wind, and there must be some sort of medium, and maybe we can test that to see how it affects us. Well, if we come up here, this is kind of the contraption they made to do the experiment, and just talking about it a little bit down here. Basically what happened is, we have a yellow, I guess that's kind of yellow. You had this light source. Should have made the sun yellow, but it's fine. I think it's actually white, but it just looks yellow. And it's emitting light rays, obviously, everywhere. And one of the light rays is going to move over here. And it's going to hit this half silver plate. And a few things are going to happen to it. Some of it's going to split up. So let me make that a little nicer. Some of it's going to just reflect up and hit this mirror. And then obviously once it hits, it's going to reflect back. Some of it might shoot, like half of it will, but the other half will go through here. And right here is this little eyepiece where we can, well, it's not an eyepiece, but it's going to detect the light coming through it. And then the same light, I'm going to use a different color just to show that it's taking a different path. Some of this light is going to go through, and it's going to hit another mirror, and then it's going to bounce back and hit this guy, and then these guys are going to merge into one light. And here's the idea. When these lights merge together, you're going to get either constructive or destructive interference. So if they're in phase, let's say we have a light wave and it's doing something like this. If it's in phase, then the amplitudes here, they'll match. So let's say let's say this is the green one. This is the green wavelength. I know it's not perfect, but the red light, it's not actually red, by the way. I'm just using that to show you the different color. It's going to be kind of matched up. This matches here. This matches here. It's not perfectly lined up, but it's supposed to at least look that way. These guys match, and you get something called constructive interference. And what does that mean? That's a bright spot. That's actually a better, and maybe it's not a better word, but I'm going to just say this. You get light. You get a bright spot. Now, the other option is you could get destructive interference. So let's say you have something like this. The other option is you could get something that looks like this. It's opposite. This peak matches with this valley. This valley matches with these peak, and they cancel out. So this is destructive interference. Destructive interference. And what does that give us? It gives us dark spots. That gives us dark spots. Now, the idea is we've done this problem before where these are the same distance, L. This is really the swimmer. It's the swimmer problem. It's the exact same thing as a swimmer problem where a swimmer goes, because keep in mind, we're going to have, we'll do this. We'll have an ether wind to think about. I don't want it to be too confusing, but we might have an ether wind that's doing something like this. And then all of a sudden, what problem do we have? We just have the swimmer problem that we worked out, where this red line is a swimmer that's going, at first it's going with the current, or with the ether wind, or with the current, right? So that was here would be C plus U, and here it'd be C minus U. It should be a C. To where this is the one kind of going off at the angle. Now, this is interesting because what did we find out? I don't want this to be too messy. What did we find out? We found that this green light should beat the red light. It should. The math works out to where if we're just using classical sense and classical transformations, this green light should beat the red light. By all logic, it should. And if that's the case, they're not going to be in phase. They're going to be out of phase. And the idea here is, if you have a dark phase, then we can kind of get an idea or calculate how quickly we're moving through this ether. We can find out the speed relative to the ether. That was kind of the idea. You could look at each change in phase is kind of what we were thinking of doing. So we're expecting, by all logic, to get destructive interference. There's very, very... Maybe if the ether winds are pointing, at a certain way, maybe they line up. But eventually, this system that we had up here, this part was like this mercury slab, and you could rotate this. So even if the ether winds line up perfectly, you can spin this and see, well, how does ether wind impact here? And they did it a lot. They did it months later, and they did a whole bunch of different stuff, every which way. So we would think they would get destructive interference most of the time. There must be, right? Because obviously one has to go faster than the other. But what did we get? We got constructive interference. Isn't that weird? Isn't that weird that no matter what they did, we always got this constructive interference at that interface there? The light was always lined up. That's weird. That's kind of freaky. And this wasn't the only experiment to the Michelson-Morrison experiment or Morley experiment. It wasn't the only one to do this. There were a lot of experiments, and no matter how hard we look, there's no evidence for an ether wind. So, what's the conclusion? There's no ether. There's no medium that light has to travel through. This stuff, it's all nonsense. Light can just travel through a vacuum. That's a weird, weird wave, man. You think of a wave in a rope. You think of a wave in water, a sound wave. You need this medium. And there's just not. Light can just travel through whatever it wants. Doesn't matter if it's a vacuum or if there's a medium. That's weird. That's really, really weird. And thankfully, pretty soon here. In fact, in the next bit we'll talk about is Einstein coming in, and he kind of really pushes modern physics here. So that'll be exciting. That's next. Hope you guys are enjoying this, and see you soon.